August 12, 1942. Chesapeake Bay, off the coast of Maryland. Lieutenant Commander James Marshall stood on the bridge of USS Cleveland, his binoculars trained on 3 radio-controlled drone aircraft circling 2 miles distant. The morning sun glinted off their yellow-painted wings as they executed lazy turns at 800 feet, waiting to become targets. Marshall had been firing at drone aircraft for 3 years. He knew the mathematics of anti-aircraft gunnery by heart. Against maneuvering targets at that range and altitude, his 5-inch guns would need approximately 40 shells to achieve 1 hit. His gunners were excellent. The guns were excellent. The problem was physics itself. A shell fired at a target 2 miles away required roughly 10 seconds of flight time. In those 10 seconds, an aircraft traveling 300 miles per hour moved nearly half a mile. The gunner had to predict where the target would be, not where it was. If the aircraft maneuvered, all calculations became worthless. Every major navy in the world faced this same impossible equation. Then Marshall received the order to load the special ammunition that had arrived under armed guard the previous evening. The shells looked identical to standard 5-inch projectiles, except for unusual markings on their noses. His gunnery officer had attended a classified briefing. The details remained secret, but the instructions were simple. Fire normally. The shells would handle the rest. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. At 08:15, Cleveland's forward battery fired its first salvo. 4 shells arced toward the drones. Marshall watched through his binoculars as the shells passed within 50 yards of the lead aircraft. Then something happened that violated every principle of ballistic warfare he understood. The shells exploded. Not at a predetermined altitude, not at a timed interval, but precisely when they reached proximity to the target. The lead drone staggered as fragments tore through its wings and fuselage. It nosed over and fell burning into the Chesapeake. Marshall's gunners, trained professionals who had fired thousands of practice rounds, stood silent at their stations. They had just witnessed something that shouldn't exist. The second drone died with the next salvo. The third managed one more turn before proximity-fused shells found it. In less than 4 minutes, Cleveland's gunners had destroyed 3 maneuvering aircraft with 4 bursts. Marshall immediately understood the implications. If these shells worked as advertised, every calculation about naval warfare had just changed. The shells were called proximity fuses, though the Navy used the deliberately misleading designation VT fuse, supposedly standing for variable time. The truth was more extraordinary than the cover story. Each shell contained a complete miniature radio transmitter and receiver, vacuum tube circuitry, a reserve battery, safety mechanisms, and a detonator, all packed into a steel cylinder 8 inches long and weighing just over 2 pounds. The technology solved a problem that every major military power had concluded was fundamentally impossible to solve. That solution came from one physicist whose approach to the impossible was to ignore everyone who said it couldn't be done. His name was Merle Tuve. Born in Canton, South Dakota, on June 27, 1898, Tuve had earned his doctorate in physics at Johns Hopkins University, studying under Robert Wood. By 1940, he was director of the Department of Terrestrial Magnetism at the Carnegie Institution in Washington, conducting research in radio wave propagation and ionospheric physics. Tuve possessed a reputation among his colleagues as brilliant, volatile, and utterly unwilling to accept limitations imposed by conventional thinking. When the National Defense Research Committee approached him in the summer of 1940 about developing a proximity fuse for anti-aircraft shells, every expert they consulted said the project was impossible. Tuve's response was to ask what needed to be done, not what couldn't be done. The problem was deceptively simple to state. Aircraft were becoming faster, more maneuvering, and more numerous. Conventional anti-aircraft fire was woefully ineffective. Statistics from the Spanish Civil War and early World War II combat showed that it required between 20,000 and 100,000 shells fired to down a single aircraft. The reason was fundamental physics. Conventional shells used either contact fuses, which required a direct hit, or timed fuses, which required accurate prediction of the target's altitude and course. Contact fuses were effective only if the shell struck the aircraft, an event requiring extraordinary accuracy or luck. The mathematical probability of a direct hit on a maneuvering aircraft at combat ranges was less than 1 in 10,000. Timed fuses were more practical but still ineffective. A gunner would estimate the target's altitude, set the fuse to detonate at that height, and fire. If his estimate was accurate and the target didn't change altitude or course, the shell would explode near the aircraft. In practice, aircraft maneuvered constantly. Pilots learned to change altitude the moment they saw muzzle flashes. By the time shells reached the predicted detonation point, aircraft were elsewhere. The concept of a proximity fuse had existed theoretically since the First World War. If a shell could detect when it approached a target and detonate automatically, effectiveness would increase dramatically. The shell wouldn't need to strike the aircraft directly. It would only need to pass within lethal range, perhaps 50 to 100 feet, and explode, showering the target with fragments. Theory was elegant. Practice was impossible. To work, a proximity fuse needed several components working in perfect coordination. First, a sensor, capable of detecting the target. Second, circuitry to process the sensor data and determine when to trigger. Third, a power source. Fourth, a detonator. Fifth, safety mechanisms to prevent premature detonation. All of these components had to fit inside the nose of an artillery shell, leaving room for the explosive charge. They had to function in extreme temperatures, survive storage for months or years, and most impossibly of all, withstand the violence of being fired from a gun. When a 5-inch shell is fired, it accelerates from 0 to 2,600 feet per second in approximately 20 feet of gun barrel. This creates acceleration forces exceeding 20,000 times Earth's gravity. For comparison, astronauts during rocket launches experience perhaps 4 times gravity. Fighter pilots in extreme maneuvers might experience 9 times gravity before losing consciousness. The components inside a proximity fuse would experience 20,000 times gravity, a crushing force that would turn conventional electronics into powder. Then the shell would spin at 25,000 revolutions per minute as it passed through the rifled barrel, subjecting every component to centrifugal forces that would tear apart anything not perfectly balanced. After surviving this violence, the electronics had to function perfectly during the shell's few seconds of flight time. The radio had to transmit signals, receive reflections, process the data, determine proximity to a target, and trigger the detonator, all while traveling at supersonic speed through air turbulence. Germany had attempted developing proximity fuses as early as 1930. Their scientists explored over 30 different approaches: acoustic sensors that would trigger on engine noise, electrostatic detectors that would respond to the charged surfaces of aircraft, photoelectric cells that would detect changes in light, magnetic sensors that would respond to steel airframes. Every approach failed. Acoustic sensors couldn't distinguish aircraft engines from gun blast or wind noise. Electrostatic detection was unreliable in varying humidity. Photoelectric cells were too fragile and couldn't distinguish targets from clouds. Magnetic sensors lacked sufficient range. German engineers concluded that radio-based proximity detection offered the best theoretical approach. A miniature radio transmitter in the shell could emit continuous waves. When these waves reflected off a target, the frequency would shift due to the Doppler effect. When the frequency shift indicated the target was within lethal range, the fuse would detonate. The theory was sound. The engineering was impossible. Radio transmitters in 1940 required vacuum tubes. Vacuum tubes were fragile glass envelopes containing delicate wire filaments heated to incandescence. Slightest shock could break the filaments or crack the glass. Surviving 20,000 times gravity was inconceivable. In 1940, Hitler's leadership issued directives prioritizing weapons projects that could reach production within 6 months. Germany's proximity fuse programs were cancelled. The resources were redirected toward projects with near-term payoff supporting the planned invasion of the Soviet Union. Some limited research continued, but it received low priority and minimal funding. Britain reached further than Germany. By 1939, researchers at the Telecommunications Research Establishment had developed working prototypes using miniature vacuum tubes from hearing aids. These tubes were the smallest available, roughly the size of a child's finger, far more delicate than standard radio tubes. British scientists tested their proximity fuses on rockets, which experienced far less acceleration than gun-fired shells. Under these gentler conditions, fuses worked perhaps 50% of the time. For military use, this was inadequate. Half of all shells would be duds. Worse, Britain's industrial capacity was already stretched to breaking point. The cost of proximity fuses would be astronomical. Manufacturing vacuum tubes small enough and rugged enough required extraordinary precision. Each tube had to be individually tested. Rejection rates would be high. Britain calculated that equipping their anti-aircraft guns with proximity fuses would consume industrial capacity needed for radar, radio equipment, and aircraft production. The British shared their research through the TISAD mission when they established scientific cooperation with the United States in 1940. They provided Americans with their prototypes, technical data, and the bitter conclusion that proximity fuses, while theoretically possible, were practically impossible given available resources. Merle Tuve examined the British research and reached a different conclusion. The fuses were possible. They simply required an approach that Britain couldn't afford. America could afford it. On June 27, 1940, the National Defense Research Committee was established under Vannevar Bush, former vice president of MIT and president of the Carnegie Institution. Bush understood that America's contribution to the war would be industrial and scientific. Britain needed weapons. America had the laboratories and factories to develop them. Bush divided the NDRC into sections, each focused on specific problems. Section T, assigned to Tuve, would develop proximity fuses. The designation stood for Tuve, though officially it meant nothing. Section T established headquarters at the Carnegie Institution's Department of Terrestrial Magnetism in Washington, but quickly outgrew those facilities. On March 10, 1942, Section T formally became the Applied Physics Laboratory of Johns Hopkins University, though it remained under Tuve's direction. The laboratory rented a former Chevrolet garage in Silver Spring, Maryland. Within months, the staff numbered over 100 scientists and engineers. By war's end, more than 1,000 people would work directly on proximity fuse development. Tuve assembled an extraordinary team. James Van Allen, a young physicist from Iowa who would later discover the radiation belts around Earth bearing his name, joined in April 1942 as a founding member. Van Allen's specialty was experimental physics. His task would be making vacuum tubes survive the impossible. Lawrence Hufstad, a nuclear physicist, handled electronic circuit design. Harry Diamond, from the National Bureau of Standards, contributed expertise in radio frequency engineering. Dozens of others brought specialized knowledge in materials science, mechanical engineering, production methods, and testing procedures. The team faced three fundamental challenges. First, develop vacuum tubes that could survive, artillery acceleration. Second, design circuits that would function reliably while spinning at 25,000 RPM. Third, create a manufacturing process that could produce millions of fuses at acceptable cost. Tuve's approach was methodical. Rather than attempting to solve all problems simultaneously, the team would tackle each challenge independently, then integrate solutions. Van Allen focused exclusively on tubes. Other groups worked on circuits, power sources, safety mechanisms, and mechanical design. Van Allen started with Raytheon and Sylvania miniature tubes designed for hearing aids. These represented the state-of-the-art in miniaturization. Each tube was roughly 1 inch long and 1/4 inch in diameter, containing a heated filament, control grids, and a plate, all sealed inside an evacuated glass envelope. Under normal use in a hearing aid, these tubes experienced gentle handling and minimal vibration. Van Allen needed them to survive 20,000 times gravity. His first step was understanding how tubes failed. He requisitioned a vertical test gun at the Naval Proving Ground in Dahlgren, Virginia. This gun fired shells straight down into soft earth, allowing recovery of intact fuses for examination. Van Allen loaded tubes into test fuses and fired them repeatedly, recovering the fuses and examining the tubes under microscopes. The failure modes were immediately obvious. The glass envelopes shattered, the filaments snapped, the internal grids collapsed, the tube elements broke loose from their mounts. Working with engineers at Sylvania Electric Products, Van Allen redesigned tubes from first principles. The glass envelopes were thickened and carefully annealed to reduce internal stresses. The filament wires were shortened and made thicker, reducing their tendency to flex and break. The internal grids were redesigned with heavier cross-sections and shorter unsupported spans. The mounting structure inside each tube was reinforced. The leads, connecting internal elements to external pins, were shortened and thickened. Every dimension was optimized for survival rather than miniaturization. After each design iteration, Van Allen fired test batches and examined the results. Gradually, success rates improved. By September 1941, tubes were surviving perhaps 30% of test firings. By January 1942, the rate reached 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness, considered this acceptable and authorized initial production. The engineers were confident they could improve reliability during manufacturing ramp-up. They were correct. By early 1943, tube survival rates exceeded 90%, but vacuum tubes represented only one challenge among many. The proximity fuse needed electrical power. Conventional batteries were too large and had limited shelf life, particularly in tropical heat where electrochemical degradation accelerated. The fuse needed to remain viable during months of storage in ships' magazines, where temperatures could exceed 100 degrees Fahrenheit, then function instantly when needed. Engineers developed what they called a reserve battery. The battery plates and electrolyte were kept separate until activation. The electrolyte was loaded into a sealed reservoir inside the fuse. When the shell was fired, centrifugal force from the shell's rotation drove the electrolyte through channels into contact with the battery plates, generating electricity instantly. This design gave the batteries effectively unlimited shelf life. Until fired, no chemical reactions occurred. Once activated, the battery provided full power within milliseconds and continued functioning for the shell's flight time of perhaps 30 seconds. The radio circuit itself required extraordinary engineering. The fuse needed to transmit continuous radio waves at approximately 180 to 220 MHz. These radio waves would reflect off any large metallic object nearby. When reflections returned to the fuse, the frequency would be slightly different due to the Doppler effect. If the fuse was approaching the target, the reflected waves would be higher in frequency. If moving away, lower frequency. By measuring this frequency shift, the circuit could determine not just that a target was present, but whether the distance was closing or increasing. When the frequency shift indicated the fuse was within optimal range, typically 50 to 100 feet from the target, an electrical relay would close, sending current to the detonator. The timing was critical. Detonate too soon, and the fragments wouldn't reach the target. Too late, and the shell would pass beyond effective range. The circuit had to perform these calculations while experiencing 25,000 RPM rotation. The centrifugal forces tried to tear every component loose. The engineers solved this by potting the entire circuit, in assembly in wax, effectively gluing all components in place. The wax also cushioned components against shock. Safety mechanisms were equally critical. The fuse could not arm until well clear of the gun. Premature detonation would destroy the weapon and kill the crew. The fuse needed protection against accidental triggering from the ship's own radar transmissions or from radio interference. It required what engineers called wave suppression circuitry to prevent premature detonation when fired at low angles over water. At shallow angles, radio waves would reflect off the water surface, potentially triggering the fuse prematurely. By the time development was complete, each Mark 32 proximity fuse for the Navy's 5-inch gun contained approximately 130 miniaturized electronic components. The completed fuse was 8 inches long, weighed just over 2 pounds, and fit into the nose of a standard 5-inch shell, leaving room for 7 pounds of high explosive. Inside, its steel casing was perhaps the most sophisticated piece of miniaturized electronics that existed in 1942. More complex than any radio, more delicate than any scientific instrument, yet designed to survive violence that would destroy conventional electronics instantly. The August 12th test in Chesapeake Bay validated everything. Cleveland's success with just 4 bursts destroying 3 maneuvering targets proved the proximity fuse worked under combat conditions. The Navy immediately authorized mass production. 5 companies were selected to manufacture fuses. Crosley Corporation, which had manufactured radios and refrigerators before the war. Radio Corporation of America, the electronics giant. Eastman Kodak, which brought precision manufacturing expertise from camera production. General Electric, with its vast industrial capacity. McQuay Norris, an automotive parts manufacturer that would prove surprisingly effective at precision assembly. Production started slowly. By the end of 1942, factories were producing 500 fuses per day. American industrial capacity was just beginning to mobilize. By late 1943, production had reached 40,000 fuses per day. The Crosley Corporation in Cincinnati alone produced 5,259,013 fuses, representing 24% of total production. The company employed 10,000 workers operating continuously 7 days per week, achieving peak output of 16,500 fuses daily. Sylvania Electric Products in Ipswich, Massachusetts produced even more. The company manufactured 5,683,332 fuses, while also producing 95% of all miniature vacuum tubes used across the entire proximity fuse program. At peak production, Sylvania employed over 5,000 workers, many of them women, assembling intricate components under microscopes. Thousands of workers signed secrecy oaths. They were searched entering and leaving facilities. They assembled components without knowing what they were building. Supervisors told them only that the devices were vitally important and absolutely secret. Security surrounding the proximity fuse was second only to the Manhattan Project. The device was given the deliberately misleading code name VT Fuse, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. Even its existence was classified. Military personnel who worked with proximity-fused ammunition were forbidden from discussing them. The very use of proximity fuses in combat was initially restricted to situations where there was no possibility of a dud shell falling into enemy hands. The Pentagon absolutely forbade use over land. The risk was too great that German or Japanese engineers might recover an intact fuse and reverse-engineer the technology. If Germany equipped its anti-aircraft guns with proximity fuses, intelligence analysts estimated bomber losses over Germany could increase by 300%. The strategic air campaign might become impossible. Thousands of bomber crewmen might die. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. So proximity fuses were used only over water, where dud shells would sink beyond enemy reach. When a proximity-fused shell accidentally landed on Sicily during the invasion in July 1943, headquarters dispatched a special recovery patrol. They found and secured the shell before German forces discovered it. This absolute security restriction seemed unbreakable. Then, in June 1944, Germany unleashed a new weapon that would force Allied commanders to make an agonizing calculation. The weapon was the Von flying bomb, and stopping it would require revealing America's most closely guarded secret. June 13th, 1944, 4:25 in the morning. Grove Road, Bow, East London. The first Vone flying bomb fell from the sky with a sound witnesses would never forget. The Argus pulse-jet engine produced a distinctive buzzing roar that gave the weapon its nickname among Londoners, the Doodle Bug. When the engine cut out, there was terrible silence as the bomb fell. Then came the explosion. The railway bridge on Grove Road was destroyed. Nearby homes collapsed. 6 people died, 30 were injured. 200 were made homeless. Over the following days and weeks, thousands more V1s would follow. Hitler called them Vergeltungswaffe, vengeance weapons, retaliation for Allied bombing of German cities. Major Walter Dornberger, head of the rocket weapons program at Peenemünde, calculated that even with a conservative 25% success rate, the Vone would deliver more explosive power to London than the entire Blitz of 1940 to 41. Each Vone cost approximately 5,000 Reichsmarks to produce, a fraction of the cost of a manned bomber mission, with no risk to aircrew. The weapon represented years of German development. The Argus AS-014 pulse-jet engine was revolutionary. The autopilot system using gyroscopes and a barometric altimeter was sophisticated. The airframe was simple but effective. The Vone flew at 400 miles per hour, at altitudes varying between 2,000 and 9,000 feet. It carried 1,850 pounds of Amatol explosive. It was the world's first operational cruise missile, and German High Command believed it would bring Britain to its knees. Dr. Robert Lusser, who designed the Vone's control system, calculated that Allied interception would be nearly impossible. British fighters needed speeds exceeding 410 miles per hour to catch the flying bombs. To destroy them, pilots had to close within 200 meters, risking destruction from the explosion. As for anti-aircraft fire, the probability of a direct hit on such a small, fast target was calculated at less than 1 in 10,000 shells fired. This wasn't propaganda, it was sound ballistic science based on conventional weapons. Within days of the first launches, British defences were overwhelmed. V1s approached at all hours, from multiple directions, at varying altitudes. Fighter pilots who managed to catch them discovered that shooting them down was extraordinarily dangerous. If the Vone exploded close to the fighter, fragments could down both aircraft. Some pilots developed the technique of flying alongside the Vone and using their wingtip to flip the flying bomb's wing, upsetting its gyroscopes and sending it into an uncontrolled dive. This required exceptional skill and nerve. Most pilots couldn't master it. Anti-aircraft guns defending London fired thousands of shells with minimal success. In June 1944, during the first weeks of the Vone campaign, British defences destroyed only 17% of flying bombs that entered the coastal gun belt. The situation was desperate. Prime Minister Winston Churchill faced an agonising decision. The V1s were inflicting significant civilian casualties. Production facilities, docks, and government buildings were being destroyed. Public morale was suffering. Something had to be done. The Americans had offered a solution: proximity-fused ammunition. The VT Fuze had been operationally successful in the Pacific since January 1943. Navy anti-aircraft guns equipped with proximity fuses were downing Japanese aircraft at unprecedented rates. But the Pentagon had absolutely forbidden use of proximity fuses over land. Churchill personally appealed to General George Marshall, U.S. Army Chief of Staff, and to President Franklin Roosevelt. He explained that London was under sustained assault. British defences were proving inadequate. Without improved anti-aircraft effectiveness, civilian casualties would mount into tens of thousands. Marshall and Roosevelt weighed the risks. Using proximity fuses against V1s meant firing them over land. Dud shells would fall where German forces might recover them. The secret would be compromised. But the alternative was allowing London to be devastated. In late June 1944, authorization was granted. Proximity-fused ammunition would be shipped to Britain specifically for use against V1s. Modified fuses were rushed into production, calibrated for the small, fast targets. Security restrictions remained absolute. Guns would be positioned along the coast. Any dud shells would fall into the English Channel. The British reorganised their entire air defence system. Anti-aircraft guns were redeployed from positions on the North Downs to the south coast, creating a concentrated gun belt. American SCR-584 radar systems provided automatic tracking. Gun crews were trained on the new ammunition with strict secrecy protocols. They were told only that the shells had special fuses requiring careful accounting. Every proximity-fused shell fired had to be logged. Unaccounted rounds would trigger immediate investigation. Naval vessels patrolled offshore, preventing any German attempt to recover dud shells from the water. By late July, proximity-fused ammunition was arriving in quantity. British and American anti-aircraft units along the coast began receiving the special shells. The effect was immediate and dramatic. As V-1s crossed the English coast, they entered a kill zone where technology trumped statistics. The SCR-584 radar automatically locked onto targets, calculated trajectories, and fed firing solutions to guns. The proximity fuses contained miniature radio transmitters, built with vacuum tubes developed by Sylvania Electric. When reflected, radio signals indicated proximity to a target. Thyrotron switches triggered detonators, sending steel fragments through the Vone's thin aluminum airframe. The flying bombs were particularly vulnerable. Unlike manned aircraft with armoured fuel tanks and self-sealing systems, the Vone was built for simplicity and low cost. A single fragment penetrating the fuel system or control surfaces could send it tumbling from the sky. Interception rates climbed rapidly. By early August, the coastal gun belt was destroying 50% of V-1s that entered range. By mid-August, the rate reached 65%. German observers on the French coast reported troubling statistics back to headquarters. At Flak Regiment 155, West technical officers struggled to understand what was happening. The mathematics didn't work. British guns were claiming kills with impossibly low ammunition expenditure. Observers watching through telescopes witnessed V-1s flying steadily toward England, then suddenly surrounded by flak bursts, then tumbling from the sky despite explosions occurring too far away for direct hits. Test firings over German territory showed normal performance. The problem manifested only against British defences. German experts began suspecting the British had developed some kind of revolutionary anti-aircraft system, but they couldn't determine specifics without captured examples. Intelligence officers offered rewards for any information about British anti-aircraft methods. Nothing useful was discovered. The Germans tried varying tactics, different altitudes, larger salvos, night launches, exploiting weather conditions. Nothing worked. The kill rate remained devastating. By late August 1944, the interception rate peaked at 74% overall, reaching 82% during one extraordinary day. On that day, August 28, 1944, British and American anti-aircraft guns along the coast fired approximately 3,000 shells at 97 V-1s approaching England. 80 aircraft were destroyed before reaching inland targets. The 17 that penetrated the gun belt were engaged by fighters or barrage balloons. The 82% destruction rate represented something German engineers had calculated was physically impossible. At Peenemünde Army Research Centre, scientists examined the reports with growing alarm. If the statistics were accurate, British defences had achieved effectiveness levels that violated fundamental principles of ballistic probability. German scientists began speculating about proximity fuses. They knew the concept was theoretically possible. German researchers had explored it extensively before the war, but they had concluded that miniaturizing radio equipment to survive artillery acceleration was impossible with available technology. Now they faced evidence suggesting the British or Americans had achieved the impossible. But without captured examples, They couldn't confirm their suspicions or develop countermeasures. The Vosne campaign continued through the summer and fall of 1944. Between June and late August, Germany launched over 9,000 V-1s from ground sites against Britain. The flying bombs inflicted significant casualties. Over 6,000 civilians were killed, nearly 18,000 were injured. But these numbers represented a fraction of German intentions. General Frederick Pyle, commanding British Anti-Aircraft Command, calculated that without proximity fuses, Vosne casualties would have been 4 to 5 times higher. London would have suffered devastation approaching the Blitz. The proximity fuse had saved the city. But using proximity fuses against V-1s meant the secret was partially compromised. Thousands of fuses had been fired over land and water near enemy-held territory. The risk that had seemed unacceptable in 1943 had been weighed against military necessity and found acceptable. In December 1944, that calculation would change completely. The context would be different, the stakes would be higher, and the decision to deploy proximity fuses would be made not by politicians in Washington or London, but by artillery officers on the front lines, who faced overwhelming enemy assault and had to make choices measured in minutes, not days. December 16th, 1944, 05, 30 hours. The Ardennes Forest, Belgian-German border. More than 200,000 German troops and nearly 1,000 tanks launched Operation Wacht am Rhein, Hitler's last desperate offensive in the West. The Germans struck through the Ardennes forest, aiming to split the Allied armies and capture the vital port of Antwerp. The offensive took the Allies by complete surprise. German forces had concentrated in absolute secrecy. The attack came through terrain the Allies considered impassable for major operations. Weather was terrible, with heavy snow and thick clouds that grounded Allied air power. Within days, German forces had driven a Bulge 50 miles deep into Allied lines. American units were surrounded, supply lines were cut, communications were disrupted. The situation was desperate. German commanders felt confident. Poor visibility made accurate artillery observation nearly impossible. Their troops could move and concentrate without facing the devastating American artillery fire that had dominated fighting since Normandy. They were catastrophically wrong. On December 16th, the same day the offensive began, Colonel Oscar Alfred Axelson, commander of the 406th Artillery Group, faced an agonizing decision. German forces were assaulting the 38th Cavalry Squadron near Monschau. The lightly armed cavalry desperately needed artillery support. Axelson had just received a new type of ammunition, proximity-fused shells, codenamed POSIT, but Supreme Commander Dwight Eisenhower had not yet authorized their use over land. The secrecy restrictions were still technically in place. Axelson decided the emergency trumped the restrictions. He ordered his gunners to fire the proximity-fused shells. The effect on German forces was devastating. For the first time in the European theatre, American artillery was firing airbursts with perfect consistency regardless of visibility or terrain. Each shell exploded 20 to 50 feet above the ground, precisely calibrated for maximum effect against personnel. The fragments spread in a cone-shaped pattern that covered an area far larger than a ground burst. Traditional artillery shells that struck the ground sent most fragments upward and outward, with the ground absorbing much of the blast. Proximity-fused shells detonating in the air sent fragments downward in a deadly rain. Foxholes, the traditional protection against artillery, became death traps. The shrapnel rained down from above, striking helmets and shoulders. Log-reinforced bunkers offered minimal protection. The fragments penetrated from overhead. German soldiers, who had survived years of combat on the Eastern Front, had never experienced anything like it. They could not hear the shells approaching due to the high velocity of American artillery. The first warning was the explosion overhead. There was no chance to take cover, no possibility of defense. The helplessness was psychologically devastating. On December 19th, 3 days into the offensive, Eisenhower formally requested authorization to use proximity fuses without restriction. The military situation was critical. German forces had penetrated deep into Allied lines. American troops were surrounded at Bastogne. The weather showed no signs of clearing. On December 21st, all limits on proximity fuse use were lifted. Over the following 6 weeks, 200,000 proximity-fused artillery shells were fired in the European theatre. The impact on German forces was immediate and catastrophic. Lieutenant General George Patton, commanding Third Army, later wrote to the War Department describing an action near the Saar River. His forces had caught a German battalion attempting to cross. Artillery fired a concentrated barrage of proximity-fused shells. By actual count, 702 enemy soldiers were killed. Patton wrote that the new shell with the funny fuse was devastating. He predicted that when all armies had this weapon, they would need to devise entirely new methods of warfare. He added, with evident satisfaction, "I am glad you all thought of it first." The morning of December 21st saw proximity fuses used in defense of Malmedy itself. SS Colonel Otto Skorzeni's Panzer Brigade 150, part of the elaborate German deception operation, attacked the town at approximately 4:30 in the morning. American artillery battalions supporting the defense fired proximity-fused shells with devastating effect. The airbursts so unnerved the attackers that some German soldiers charged directly into American positions, seeking any shelter from the overhead explosions. The attack was repelled by afternoon. German prisoners of war interviewed by American intelligence officers captured the psychological impact. One German artillery officer, captured in January 1945, described the proximity fuse as demonstrating a fundamental difference in industrial capacity. American engineering, he said, solved impossible problems through massive application of resources. The proximity fuse required extraordinary manufacturing capacity and acceptance of high costs. Germany could never have produced such a weapon, not because German engineers were less skilled, but because German industry could not support the required infrastructure. Another prisoner, a Luftwaffe engineer, focused on the implications for air defense. If Germany had possessed proximity fuses, he estimated the Allied strategic bombing campaign would have become unsustainable. At loss rates of 15 to 20% per mission, the combined bomber offensive would have ground to a halt, but he immediately added that Germany could not have developed it with available resources. The proximity fuse required an economy that could allocate billions of dollars to a single weapon system and mobilize over 100 factories for production. Only America possessed such capacity. German soldiers experiencing proximity-fused artillery fire faced a more immediate revelation. They were being killed by technology they could not comprehend, produced in quantities they could not match. Traditional defensive positions were suddenly death traps. Moving in the open during artillery fire was suicide. The Germans tried to adapt by dispersing more widely and staying constantly on the move. But adaptation had limits. The proximity fuse fundamentally altered the tactical equation. Some German units experienced discipline problems, with soldiers refusing orders to move into areas under American artillery coverage. American intelligence reports noted that German commanders were offering rewards for intact proximity fuses, hoping examination might reveal weaknesses or provide insight into countermeasures. Wright Field in Ohio developed electronic countermeasure systems designed to jam the fuse's radio signals, based on the assumption that captured fuses would lead to German jamming efforts. But German engineers, even when they captured intact proximity fuses, never fully recognized what they had. Having concluded years earlier that radio-based proximity fuses were impossible given artillery acceleration forces, they never grasped that miniature radio transmitters were inside every shell. Some German technical officers who examined captured American shells reported finding what appeared to be radio components in the nose fuses, but their reports were dismissed as misidentification. The prevailing assumption was that Americans were using improved mechanical time fuses, or perhaps barometric fuses that detonated at specific altitudes. The intellectual framework that had led German scientists to conclude proximity fuses were impossible prevented them from recognizing proximity fuses when they literally held them in their hands. This represented one of the war's most significant intelligence failures. From January through March 1945, as Allied forces advanced toward the Rhine and into Germany itself, proximity-fused anti-aircraft fire brought down more than 1,000 German aircraft. Luftwaffe pilots reported shells that seemed to explode whenever they approached, regardless of altitude or maneuvering. What had been dangerous but survivable anti-aircraft fire became a nearly impossible barrier. Ground combat intensified as well. During Rhine crossing operations, American artillery fired tens of thousands of proximity-fused shells, creating such concentrated destruction that German defenders were unable to mount effective resistance. The shells were particularly devastating in urban warfare. Proximity fuses set to detonate at rooftop level showered entire city blocks with shrapnel, making defensive positions untenable. German forces that might have held urban areas for days or weeks were forced to withdraw after hours. General Eisenhower, writing after the war, acknowledged the contribution of the proximity fuse in stark terms. He suggested that if Germany had succeeded in perfecting and using proximity fuses 6 months earlier than the Allies, the invasion of Europe might have proven exceedingly difficult, perhaps impossible. The counterfactual was chilling. German anti-aircraft defences equipped with proximity fuses might have made D-Day naval bombardment and air support unsustainable. German artillery using proximity fuses during the Normandy campaign could have inflicted casualties that halted the Allied advance. Technical intelligence gathered from captured German documents after the war revealed the full scope of German proximity fuse research. German forces had indeed developed more than 30 different approaches, some remarkably sophisticated. The Kranich acoustic fuse used a mechanical tone filter connected to a resonating reed switch. Rheinmetall Borsig developed an electrostatic fuse using capacitive detection. There were optical fuses, magnetic fuses, and experimental radio fuses similar to the American design, but none had advanced beyond limited testing. When research resumed at Rheinmetall in 1944, hundreds of working prototypes were developed and test-fired. But by then, it was far too late. Germany lacked the industrial capacity to establish mass production. Even if production facilities could have been created, the resources required would have competed with production of tanks, aircraft, and basic ammunition. The German war economy was already strained to breaking point. Allocating resources for proximity fuse production would have meant cutting production elsewhere. The American proximity fuse program succeeded because it had resources that dwarfed the entire German military research budget. The proximity fuse alone consumed over $1 billion 1940s dollars. This included not just research and development, but building dedicated production facilities, training tens of thousands of workers, and maintaining absolute secrecy around the entire program. The production statistics were staggering. At peak output, American factories were producing 70,000 fuses per day. That represented nearly 3 billion individual components manufactured to precise specifications, assembled, tested, and shipped to combat theaters around the world. The cost per fuse fell dramatically as production expanded. In 1942, each fuse cost $732. By 1945, mass production techniques had reduced the cost to just $18 per fuse. This 97.5% cost reduction resulted from manufacturing innovations, increased efficiency, and economies of scale. At $18 per fuse, the weapon was expensive but not prohibitively so. The increased lethality justified the cost. A proximity-fused shell was worth 5 to 10 conventional shells in terms of target effect, since the shell itself cost the same regardless of fuse type. Paying extra for a fuse that multiplied effectiveness was obvious value. The secrecy was so complete that production workers at different factories did not know other facilities were building the same components. Suppliers manufactured parts without understanding their purpose. The security classification remained in force until September 1945, when the war ended and the proximity fuse was finally revealed to the public. For German prisoners of war, who had witnessed proximity-fused fire, the revelation of what they had faced was profound. Interviews with German soldiers conducted in 1946 after repatriation captured this understanding. One former Wehrmacht officer described the proximity fuse as the weapon that finally made him comprehend Germany had lost the war, not because of the fuse itself, but because of what it represented. The fuse was a solution to a problem that Germany had concluded was unsolvable. It required industrial capacity, scientific sophistication, and economic resources that Germany could not match. If America could build miniature radios that fit inside artillery shells and worked after being subjected to forces that would destroy normal electronics, what else could they build? The officer's conclusion was that Germany had been fighting a war of the 20th century with outdated assumptions about what was possible. The proximity fuse demonstrated multiple technological advances working in coordination. Miniaturized vacuum tubes required breakthroughs in materials science, particularly in glass composition and annealing techniques. The printed circuit boards were among the first mass-produced examples of a technology that would revolutionize electronics. The reserve battery design using centrifugal activation was innovative. The radio circuitry was elegant and efficient. But perhaps the most significant advance was in manufacturing and quality control. Producing millions of complex electronic devices with consistent quality-required systems and processes that barely existed before the war. American industry developed statistical quality control methods, automated testing procedures, and supply chain management systems that would become foundations of modern manufacturing. The workforce training programs were equally significant. Tens of thousands of workers, many with no technical background, were trained to assemble intricate electronic devices under microscopes. Young women who had worked in textile mills or department stores became precision electronics assemblers, working to tolerances measured in thousandths of an inch. The knowledge and skills developed during proximity fuse production would transform American industry after the war. James Van Allen, the physicist who helped develop rugged vacuum tubes for proximity fuses, later applied the same miniaturization techniques to scientific instruments for space exploration. The Explorer 1 satellite, launched in 1958 and credited with discovering the Van Allen radiation belts, used instruments that drew directly on proximity fuse technology. The knowledge gained from making electronics survive artillery acceleration helped make electronics that could survive rocket launches into space. The technology transfer went beyond space exploration. Engineers who had worked on proximity fuses went on to careers in the electronics industry, bringing expertise in miniaturization, quality control, and mass production. The proximity fuse's military impact extended through the Korean War, where American forces used improved versions against enemy aircraft and ground forces. Modern weapon systems use descendants of the World War II proximity fuse. The Phoenix missile, the Standard Missile family, and the Patriot surface-to-air missile all use proximity fuses based on the same fundamental concept developed in 1942. Today's fuses use solid-state electronics, microprocessors, and sophisticated signal processing. They can discriminate between real targets and decoys and operate in jamming environments. But the core principle remains unchanged. Detect the target using radio reflections, calculate the optimal detonation point, and trigger the warhead for maximum effect. The broader lesson extended beyond the proximity fuse to the entire character of American military production during World War II. America outproduced the Axis powers not just in quantity, but in quality and sophistication. American weapons were not always individually superior to German or Japanese counterparts, but American weapons worked reliably, were produced in overwhelming numbers, and included technological innovations like proximity fuses that gave critical advantages. The combination of quantity and quality was what made American production decisive. The proximity fuse provided a force multiplier that turned numerical superiority into overwhelming dominance. By the final year of the war, German forces were facing enemies who had better weapons, more weapons, and technological advantages that made traditional tactics obsolete. The casualty statistics reflected the impact. During the Battle of the Bulge, despite initial surprise and favorable terrain, German forces suffered disproportionate casualties. American artillery was responsible for an unusually high percentage of German losses. Medical personnel reported that wounds from proximity-fused shells tended to be more severe than wounds from traditional artillery. The shrapnel came from above, targeting the head and shoulders. Multiple fragment wounds were common. The lethality was significantly higher. By March 1945, as Allied forces prepared to cross the Rhine and advance into Germany, proximity-fused ammunition had become standard for all American artillery. Factories were producing fuses faster than they could be shipped to Europe. The Germans never developed effective countermeasures. Electronic jamming was theoretically possible, but required understanding the fuse's operating frequency and characteristics. Without intact working fuses to analyze properly, German engineers could not determine the specifications needed for jamming. Even if they had, deploying jammers across every potential target area would have been impossible. Physical countermeasures were equally ineffective. The fuses, operated by detecting reflected radio waves, reducing the radar cross-section of troops and equipment was impossible. The human body itself reflected enough energy to trigger the fuse at close range. The only defense was dispersion, spreading forces widely enough that a single shell would not catch multiple targets. But dispersion reduced combat effectiveness and made coordinated operations difficult. German tactical doctrine had evolved around concentrated formations. Dispersing to counter proximity fuses weakened overall capability, even as it reduced casualties per shell. The final months of the war saw some German units essentially paralyzed by fear of American artillery. Units would not move during daylight. They avoided any position that appeared to be a likely target. Morale plummeted. The sense of helplessness broke the will to resist. American intelligence reports noted that German prisoners increasingly cited artillery as the primary reason for surrender. Not the fear of death, which soldiers accepted, but the specific fear of proximity-fused artillery, which provided no chance of survival and no way to fight back. This was psychological warfare at its most effective, accomplished not through propaganda, but through demonstrated futility of resistance. Post-war analysis by military historians identified the proximity fuse as one of the key technological advantages that shortened the war. Estimates suggest the fuse saved tens of thousands of Allied lives by reducing the length of campaigns and increasing effectiveness of defensive operations. Against kamikaze attacks in the Pacific, proximity fuses were credited with preventing ship losses that would have significantly delayed operations. The strategic impact was multiplied by production scale. Because fuses were available in unlimited quantities by late 1944, they could be used without conservation. Fire missions that would have been questionable with conventional ammunition became routine. Suspected enemy positions could be saturated. Defensive fire plans could cover vast areas with overlapping patterns. The psychological effect of this abundance was as significant as the physical effect. The story of the proximity fuse is ultimately a story about one physicist who refused to accept conventional wisdom about what was impossible. Merle Tuve's approach to the problem was fundamentally different from the European scientists who had concluded proximity fuses couldn't be built. European researchers approached the problem by asking what was theoretically possible given existing technology. Tuve approached it by asking what needed to be done, then figuring out how to do it. When told vacuum tubes couldn't survive artillery acceleration, he didn't accept that limitation. He redesigned vacuum tubes until they could survive. When told miniature radios couldn't fit inside artillery shells, he didn't accept that limitation. He designed radios that fit. When told the cost would be prohibitive, he didn't accept that limitation. He designed for mass production that would drive costs down. This approach reflected a peculiarly American mindset during World War II. Problems existed to be solved through application of resources and engineering ingenuity. Theoretical impossibility was merely a challenge requiring creative solutions. The proximity fuse stands as testament to what free societies can achieve when they combine scientific excellence with industrial might and unwavering determination. It proved that the greatest victories come not from seeking wonder weapons, but from making necessary technologies work through sheer force of will and unlimited application of resources. Over 22 million proximity fuses were produced during World War II. Each one represented Merle Tuve's refusal to accept impossibility. Each one contained components that German scientists had concluded couldn't be manufactured. Each one worked with reliability exceeding 90%, despite conditions that should have destroyed it. The German soldiers who faced proximity-fused fire understood this, implicitly. Wehrmacht veterans interviewed after the war consistently described the Fuze, not merely as a clever weapon, but as a demonstration of comprehensive superiority in science, industry, and national will. The proximity fuse ended their war not through any single dramatic defeat, but through the accumulated weight of countless engagements, each proving the same lesson. They were fighting an enemy with capabilities beyond their ability to match or counter. That realization, more than any battlefield loss, broke the Wehrmacht's spirit and hastened the end of the Third Reich. The weapon that had seemed impossible to build became the weapon that changed warfare forever. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.